Hey everyone, welcome into lecture number 4 of Calculus 3. This lecture is on motion in space. Let's start off by writing down some definitions. So let's suppose that we have a vector function r, and that this vector function represents the position function of a particle moving in space. So suppose r is the position function of a particle. Now, a particle in this sense could be very large. It could be a spaceship or anything. So we're just going to call it a particle, position function of a particle. Then we know a couple of things. We've made a definition before that the derivative with respect to time, r dot I call it, but dr dt, that is the velocity of the particle, right? So the velocity, this is what we're defining, of the particle is then given by the vector function v of t, which is dr by dt as a function of t, right? Which in simplified form, we've just been writing as r dot of t. Or you could write r prime of t if you wish. Okay? If you've taken some physics, then you probably can guess that the acceleration of the particle is going to be the second derivative of the position function, or the first derivative of the velocity. Okay, so this will be the acceleration of the particle. And again, this is going to be a vector function. This is given by a for acceleration of t. It's a vector function. It's defined to be dv by dt, so the derivative of velocity, which again, we could just write this as v dot of t, and because v itself is r dot, then this just becomes r double dot. So second derivative of r is our acceleration function. Okay, now there's one more thing that we would like to define here. The magnitude of velocity is called the speed, and we're going to write down kind of a simplified way to write this function. So the speed of the particle, and we talked about this in the last lecture actually. We use this idea. You'll see it's going to be very familiar. But the speed of the particle is the magnitude of velocity. So it's going to be v of t. I wrote this kind of like a script v without a hat. Okay, this is a scalar function, and it's going to be defined to be the magnitude of the velocity, which, as we know, can be written as the magnitude of r dot dt. And this is something that we talked about in the last lecture. Magnitude of r dot times dt, that would be the arc length element, right? And that dt represents a tiny change in time, which is why you end up with length instead of speed, right? But as it's written here, the speed function, v of t, for our particle is just the length of r dot of t. So that's going to end up being a scalar function. Okay, well, those are our definitions. Those are the main definitions of this lecture. We'll get into breaking up the acceleration into components a little bit later on, so that'll be the kind of the grand finale. But for now, let's just take a moment and compute some examples here. So this will be item 2. I'd like you guys to find the velocity, speed, and acceleration of the following vector function. So this is just computations, right? Just using this new vocabulary. I want to find the velocity, speed, and acceleration of the particle with this position function. So the position function here is going to be r of t equals square root of 2 t I, so only the 2 is under the square root there, then plus e to the t j, and then plus e to the minus t k. All right, so why don't you guys take a moment, work on this one, try to simplify your vector functions and your scalar function for speed as much as possible, and then when you hit play again, we'll reconvene and do this one together. Okay, now that you've had a chance to work on this one on your own, let's work through it here. So here's our position function of our vector. I'm going to rewrite this in kind of the angle bracket form, just to get rid of the ijk. There's nothing wrong with the ijk, but I personally just like to look at it when it's not in this form. So here's our vector function, our position function, r of t. We want to compute the velocity function. We'll go in this order, right? Because we need to know the velocity before we can compute the speed. And then we could do either acceleration or speed in either order, right? But we'll do it in the order that we were given. So our velocity vector is going to be, again, r dot of t. That's the derivative with respect to t. And as we go through here, this is going to end up being constant square root 2. Derivative of e to the t is itself. Derivative of e to the minus t is minus e to the minus t. So there's our velocity, right? So I'll highlight this. This is our velocity vector function for this particle. All right, now we want to find the speed. So the speed, oh boy, the speed should not have a hat, right? It's a scalar function. This is the magnitude of the velocity. And as we know, the formula for the magnitude is to square the terms and then add them up, right? So we're going to end up with square root and then square root the whole thing. But square root of 2 squared plus e to the t squared plus e, so this is plus negative e to the minus t quantity squared. And as we work this out, I'm going to rearrange a little bit. But this one's going to be e, I'm going to write it this way, e to the t squared plus 2 plus e to the minus t squared. This is not right. I meant to put parentheses here. E to the minus t. So the minus sign gets squared out, right? The minus sign in front of this. But I want to write it like this. If you were going to combine those, it would end up being e to the minus 2t, not e to the minus t squared as I had written it, right? So the squared has to go here. And now it turns out that this factors actually. So this can be written as e to the t plus e to the minus t quantity squared underneath this. So I'll let you guys verify this, but e to the t plus e to the minus t quantity squared. If you distribute this out, you multiply this out, you'll end up with exactly this, right? And then a square root and a square. This term is always positive, right? E to the t, e to the minus t, that has to be positive. You can't get any negatives out of that. So what we end up with then, I mean, I'll write the absolute value because by definition that's what it is. But because this term is positive, what we end up with is a formula for our speed function is just going to be e to the t plus e to the minus t. All right, so we'll highlight this one as well. But there's the speed of our particle. And then the last thing that we want to do is compute the acceleration. So for the acceleration, we go back to our velocity vector. And we remember the a of t, this is going to be just v dot, which is r double dot, but we've already got this in terms of v, so we can just leave it like this, right? The derivative of square root 2, that's a constant, so it's just 0. E to the t is itself, and then another derivative here is going to make this positive again, right? So the acceleration is e0, e to the t, e to the minus t. And that's it. So that'll be our acceleration function of our particle. So here we have velocity, we have speed, we have acceleration. That's what we were asked for. So we're done. All right, I've got another example here for us. Computational example. This one is going to give us the acceleration of the particle. So we'll call this item number 3 of the lecture. So I would like to try to find the position function of the particle that satisfies the following information. And I'll write it down here. So satisfying the following information. We know that the acceleration function, we're given, I should say, that the acceleration function is 2t I plus sine of t j plus cosine 2t, so cosine of 2t k. And we're given some initial data on the velocity and the initial position of our particle. So the initial velocity of our particle, initial just means here that t is equal to 0 when this happens, right? But the initial velocity is just going to be the vector I, so 1i plus 0j plus 0k. And then the initial position of our particle is going to be 0i plus 1j plus 0k. So it's just j, the unit vector j. So again, take a moment on this one. Try to think through how you could undo the acceleration and get back the position, and then use these initial data to help you along the way. And I'll check back in with you in a moment. All right, so let's check in and see how you did now. remember that the acceleration is the second derivative of position, but it's the first derivative of velocity. So actually what we can do here is kind of solve a couple of different differential equations, very simple differential equations. But remember, our a of t, that's actually dv, I'm going to write it this way, dv by dt of t, right? It's a function of t, but that's given by this vector function, 2t sine of t cosine of 2t. And so that means that our differential of velocity, dv, is equal to this differential vector, 2t sine of t cosine of 2t, all times dt. And at this point we can integrate. So we know how to integrate our vector functions. We do it component by component, right? So on our left-hand side, what we end up with here is we have our v of t. And then remember, we integrate component by component, but each component gets its own unknown constant as we go along, right? Or we could add an unknown constant vector at the end of it. So I'll do it the second way I said, but the antiderivative of 2t is t squared. The antiderivative of sine is minus cosine. And then the antiderivative of cosine 2t is 1/2 sine of 2t. All right, and then we have our vector of unknown constants added to the end of this. And now we need to deal with this, right? So how can we deal with this vector of unknown constants? Well, we need to plug in our initial condition here. So we also know that v of 0 is equal to the vector I. So the vector I in component form is 1, 0, 0, right? So that's our given information. But what we can do then is plug into our given vector function up here that we just found and determine what must these constants be in order to get this, right? So on one hand we have that. On the other hand we have that this is going to be 0 squared and then minus cosine of 0, 1/2 sine of 0, plus again c1, c2, c3, vector of unknown constants. And then when we add this all up, this one is going to be 0 plus c1, so that's just c1. This one's going to be negative 1 plus c2, right? And this one's going to be 0 plus c3. You just plug in 0 and see what you get. So now we have a couple of equations, right? So we have that our c1 must equal 1. We have negative 1 plus c2 must equal 0. And then we have c3 must equal 0, right? And so at this point we can write down our equation for our velocity. So velocity is now going to be, this means, by the way, so c1 is 1, c2 is also 1 because of this relationship, right? c2 minus 1 has to equal 0, so c2 must be 1. So at this point I'm going to take these constants and I'm going to add them component-wise. So we now end up with what? T squared plus c1, so t squared plus 1 in the first component. In the second component we're going to have minus cosine of t plus 1. And in the third component we're going to have plus this constant 0, right? So just 1/2 sine of 2t. All right, and then we just repeat everything again to get rid of the derivative of velocity and get our position function. So same idea, right? So now we're going to write dr by dt is equal to this, and so we can kind of do two steps at once here. Here's our vector function, our differential, our vector differential, because I'm going to add the dt over here, right? And then we can integrate both sides, and look what we've got here. R of t is going to be equal to, this one's going to be 1/3 t cubed plus t plus c1. I'll just put the c's in the vector on this one, the unknown constants. This one's going to end up being, so antiderivative of cosine is sine, so this is minus sine of t plus t plus c2, and then this one's going to end up being minus 1/4 cosine of 2t plus c3. All right, and our initial data, so let's plug in 0 to this one first of all. It's going to involve 0 again, so when we plug in 0, we're going to get 0 plus 0 plus c1. Here we're going to get 0 plus 0 plus c2, so that's c2. And here we're going to get negative 1/4 times 1 plus c3. So this is negative 1/4 plus c3. So that's just plugging 0 into this function. But we also need to then use this given information, right? The initial data. R of 0, we're told, should be j. So on the other hand, our given information is that r of 0 is equal to j, which is 0, 1, 0, right? And so once again, we just kind of match up these components. C1's got to be 0, C2's got to be 1, and then because of this relationship, C3 is going to be a quarter, 1/4. And so our final answer here is that our position function of our particle with the given information is going to be 1/3 t cubed plus t plus 0, so that's it, minus sine of t in the second component, minus sine of t plus 1, right? And then in the third component, it's going to be minus 1/4 cosine of 2t plus a quarter, right? Because that's what we found for C3. And so there's our answer. Okay, so that's how you compute these so the position functions of a particle given the acceleration and then some initial data. So the initial data was the initial velocity and the initial position of our particle up here, right? So that was the given information. All right, so let's talk a little bit more about acceleration now as item 4 here. We would like to break down the components of acceleration. So in other words, I want to know exactly where does the acceleration point, right? So let me draw a little sketch of a space curve here. So here's a curve. We'll consider this to be the position function of our particle. If we are, say, at this point, then we know exactly what the velocity vector looks like, right? So if the particle is moving in this direction around the curve, the velocity vector is going to be tangent, right? It's going to be tangent, and it's going to look like this. But the question becomes, what does the velocity vector look like, right? So, sorry, that is the velocity vector. What does the acceleration vector look like? So in what direction does the acceleration vector point? So let's do a little bit of analysis here on just the functions that were used to build our velocity vector, so the vector functions. And then we can try to sketch up here exactly what our acceleration is going to look like. So let's remember, first of all, that our unit tangent vector field, so I'm just going to kind of write some stuff that we already know here, right? So I'm going to write this. We have our unit tangent vector field is given by r dot of t, one of the formulas for it. This isn't the definition, right? But it's one of the formulas for it. It's given by r dot of t over the length of r dot of t. But in our definitions that we've given in this lecture, r dot is our vector v, that's our velocity, right? And the length of r dot is our scalar function speed, right? It's little v of t. And so just by rearranging this a little, and remember, in general, we assume that our vector functions are smooth, our position functions. And remember, this means that r dot of t is not equal to the 0 vector on its domain. So which means the speed is not 0, right? The speed's not 0. So what we can do then is just multiply both sides by the speed, little v of t, or regular v of t here, and we end up with a new formula for our velocity. So our velocity is then going to be equal to the product of the speed as a function of t times the direction, the unit tangent vector field, as a function of t. Okay? Now, why is this useful? Well, we have defined our acceleration, right? We've defined our acceleration to be the derivative of velocity. All right, and so therefore it's going to be the derivative, if these are equal to each other, it's going to be the derivative of this product function. So v of t times t of t. And remember, the product rule applies here. We've got a scalar function times a vector function, but we have to apply the product rule. And so this is going to give us v dot of t, derivative of speed, which is like the one-dimensional acceleration in some sense, right? Times the tangent vector field. Plus, then we have to leave the first function, the velocity, alone and take the derivative of the tangent vector field. So that's going to be times t dot. All right? So at this point, we see that we've got our acceleration. It comes in kind of two components. This component is a scalar function, v dot, times the direction vector of the tangent vector field, right? So this is going to be the tangential acceleration. So in other words, this portion of the acceleration is going to be in the same direction as our velocity. The acceleration is going to be the same. This right here is different though, right? So this component of the acceleration is different. and we need to analyze exactly what direction this points in. And we see a t dot here, right? In the last lecture, we used the fact, so it was a couple lectures ago that we proved the fact that t dot must be perpendicular to t, right? In the last lecture, we used that fact to define a new normal unit vector field, which I just gave away. It's called the normal vector field, right? So let's remind ourselves of how we define that, right? So we recall now that one of our definitions, or the definition of the normal vector field, the unit normal field, was that it is given by the derivative of t, so t dot, divided by the length of t dot. So that's what made it a unit vector field. So I'm just going to write in our function of t here. Just remind ourselves that everything here is a function of t. All right. And another fact that we have is that the length of t dot, I hope we remember. So let me write it this way. So we have the curvature function as well, right? So here's where this one is the one that we have many, many different formulas for. So the curvature function, one of the formulas for the curvature was that it is given by the length of t dot divided by the length of r dot. All right, and again, these are functions of t. I didn't write the t here. But the whole point here is that, okay, well then we can rearrange and solve this for the length of t dot. So the length of t dot of t is going to be equal to this. But remember, this is our speed, right? So this is our speed and this is our curvature. So the length of t dot is equal to the velocity, or the speed function times the curvature function. And now what we can do is take this, plug it in over here, and solve for t dot, because that's what we really want. We really want to know what's t dot, right? So taking all of this together, here's what we get. The vector field t dot of t, it's going to be equal to the length of t dot of t times the normal direction field, unit normal field, which is then equal to the velocity, the speed, I keep saying velocity because it's a lowercase v, the speed function times the curvature function, that takes care of the length of t dot, right, times the unit normal direction. And then this has to go back in up here, so there's another speed, right? There's another speed, another v of t that has to go into this. All right, and so this one, yeah, we'll plug this in up here, but this is going to be called the normal acceleration, because now we can see that it's going to be in the direction of the normal vector, right? The normal acceleration. So let me write down everything that we've done, and then I'll go back to the picture and draw something. But what we've determined then is that the acceleration of the particle lives in the plane determined by t and n, right? So its components are t and n. So it lives in the oscillating plane. So, or lies in the oscillating plane. That's the one determined by the tangent vector and the normal vector. Remember, the normal vector points in the direction of the curvature, right? So it lies in the oscillating plane and is given by this formula. So our acceleration with respect to t is equal to the derivative of speed. So v dot times the unit tangent vector, so that's the tangent component, plus speed squared, so v squared, times the curvature, kappa of t, times the normal direction. All right, and so these are the components in the oscillating plane. So let's give these things a couple of names here. So I think I did this one in blue up there. We're going to call this the tangential component of acceleration. This is a scalar function. This is just v dot, so the derivative of speed. So that's like the one-dimensional acceleration if there's no curvature, right? That's what we're used to as being acceleration, derivative of speed. It's not derivative of speed, right? It's derivative of velocity in reality. All right, and then this component function right here, this is going to be the normal component of acceleration. Again, it's a scalar function, but it's equal to speed squared, so v squared, times the curvature, so kappa of t, curvature. All right, and if we go back up to our picture, how do these things work, right? Well, we're going to end up with something like at times the tangent direction here. So there's our, just for the sake of this picture, this is the tangential acceleration. And then the normal acceleration, remember the normal vector points in the direction of curvature. So this one will be like the normal component times n. And then remember how vectors work. If we have two components, then we can add them together with the resultant method, right? And the acceleration kind of points like this. So here's our A, acceleration as a whole. It's the sum of the tangential acceleration plus the normal acceleration at that point. Okay, so it's got a component in the direction of curvature, a component in the direction of the velocity, and altogether the acceleration is kind of pulling in this diagonal direction in relation to the two of them. Okay, so again, these are called the component functions of the acceleration. We have the tangential, we have the normal. Let's actually compute one here. But before we do, let's try to get these. So it would be nice if we could compute these with respect to only the r vector itself, right? The position vector. So if we didn't have to go through the steps of finding the curvature, mostly that's the one that takes a little bit of work. But finding the curvature, finding the speed function. So let's write down some formulas here for computing these with respect to r only. So that's going to be our next step. Computing the components of acceleration with respect to the position function r only. So that's our job, and without having to reparameterize, right? So the first thing that I'd like to do is just notice that if we take the dot product of v with a, then we get something nice. So let's notice that if we took v dot product with a, let's see what happens. Well, we know that v, based on our work up above, right? So let's just go back here. V is equal to speed times the tangent vector, right? So this is going to be scalar function v of t times tangent direction field dotted with the normal is all this stuff, right? I don't have to scroll, it's right there. So that's going to be v dot of t times tangent vector t plus this, speed, v squared, speed squared, times curvature times the normal vector, direction of t. And remember the dot product distributes, right? So we end up with, I'm going to drop the t's, the little t's now, because everything's a function of t here. So this is going to end up being v times v dot times t dotted with t, right? Plus, this one's going to end up being v times v squared times kappa, so v cubed kappa times t dotted with n. Right? And now we need to use some of the properties that we know. The tangent vector field is a unit vector field, so this dotted with itself is equal to 1, right? So any unit vector field dotted with itself is equal to 1. And the way that these are defined, t and n are orthogonal, right? So this is equal to 0. So what we have now is that the dot product, v dotted with a, is just equal to velocity it's equal to speed times the derivative of speed, right? V times v dot. All right, now what we can do is plug in our formulas for r into this one, right? So we can write down exactly what this is. Remember, v dot is our component function for a sub t, the tangential component of acceleration. So, a sub t. So tangential component of acceleration is then, if we just solve for this, right? Well, we know it's v dot of t. Just solving for this, it's going to end up being v acceleration, velocity dotted with acceleration, v dot a over speed, lowercase v. But we know what all these are in terms of r, the position function. Velocity is r dot, acceleration is r double dot, and speed is the length of r dot, right? So this ends up being r dot dotted with r double dot divided by speed, so length of r dot. All right, and so this gives us a formula for the tangential acceleration in terms of only the position function. So there we go. We can just go straight to that when necessary, right? All right, Similarly, we can write down something. We already know a formula for the curvature and the speed squared with respect to the vector function r. So we can then just write down the following. We know that since kappa is given by the following formula, right? Kappa is the length of r dot crossed with r double dot divided by the length of r dot cubed, right? The arc length cubed, or the speed cubed. And we've already talked about this, right? That v squared, the speed squared, is the length of r dot squared. Then very simply, we can just write down the normal acceleration function with respect to t, which again is equal to v squared times kappa. This is just going to end up being the length of r dot crossed with r double dot divided by the length of r dot to the first power, because these two will cancel. So, all right, and we end up with this formula for the normal component of acceleration, length of r dot crossed with r double dot divided by the length of r dot. All right, so the tangential acceleration component is given by the dot product up here, r dot dotted with r double dot divided by length of r dot. The normal component is given by the cross product, right? So r dot crossed r double dot, but then to make that a scalar function, you have to take the length of that, the magnitude of that. Okay, so let's just finish this lecture by doing one more example, and we'll leave it there. And this will be item number 6. So I would like to compute the component functions of acceleration. So a sub t and a sub n for the following. This is just r of t equal to t times I plus 2e to the t j plus e to the 2t. Okay. All right, so why don't you take a moment, work on that one, and then we'll check back in a moment. All right, so let's see how we did. We are just going to plug into these formulas. So in these formulas, we just need to know r dot and r double dot, and then we can use those two formulas that we just worked out, right? So let's write r in angle bracket form to start with. It's going to be 2 e to the t, 2e to the t, and then e to the 2t. So r dot is then 1, 2e to the t, and then 2e to the 2t. And r double dot is going to then be 0, 2e to the t, 4e to the 2t. All right. A couple things here. We need to do r dot, the length of r dot, right? This shows up in the denominator of both of them. So this one's going to be the square root of 1 squared plus 2e to the t squared plus 2e to the 2t squared. So this is the square root of 1 plus 4e to the t, sorry, e to the 2t. Right? And then plus 4e to the 4t. So at this point, we notice that this actually can factor. So this term right here is the square of this term. So this ends up being the square root of 1 plus 2e to the 2t quantity squared. If you multiply this out, again, kind of similar to what we did on the previous one, you'll find that this is correct, in fact, right? And then again, we can take the square root and the square, they can cancel. This will end up being positive, so this is 1 plus something positive, so it's definitely positive. And we end up with our length of r dot, or our speed, is 1 plus 2 e to the 2t. So there's our function for that. Then we need to take both the dot product and the cross product, and then find the length of the cross product, right? So let's work on that next. So r dot dotted with r double dot, we'll take the dot product first. And this one's going to be just component by component, right? So we can just take these component by component and then add them up. So it's going to be 0 plus 4e to the 2t plus 8e to the 4t. All right, so that's just working out the dot product. The cross product is going to be, so r dot crossed with r double dot. The first component is going to be 8e to the 3t minus 4e to the 3t. So that leaves us with 4e to the 3t. The next component is going to be 0 minus 4e to the 2t. And then the last component is going to be 2e to the t minus 0, right? So just 2e to the t. And then we need the length of this vector. So the length of the cross product is going to be 16 e to the 6t plus 16e to the 4t plus 4e to the 2t. And so if nothing else here, we can factor out a 4e to the 2t from everything, right? So when that comes out, that's going to be 2e to the t times the square root of what's left. So we're taking out 4e to the 2t from each, right? So this is going to be 4e to the 4t plus 4e to the 2t plus, that's going to leave us with 1. And this is exactly what we did right here, right? So we already know exactly how that works. It's just in a different order, but it's the exact same term. So this is just going to be 2e to the t times our function here, 1 plus 2e to the 2t. And we can write out our components of acceleration then, right? So we know our a sub t, that's the one that's built from the dot product. So that one's going to just be, I'll just write out everything we need here, right? So it's the dot product divided by the speed. So this one's going to be 4e to the 2t plus 8e to the 4t divided by 1 plus 2e to the 2t. We'll just leave it like this. You could factor some stuff on the top, but nothing's going to cancel, I don't think. Actually, it will, won't it? So don't jump the gun, because a 4e to the 2t can come out of this, right? 4e to the 2t, and look what's left when you do that. It's 1 plus 2e to the 2t, and that's going to cancel. So this term is just 4e to the 2t. So our tangential acceleration is 4e to the 2t, and our normal acceleration, well, that's going to be this, right? So it's 2e to the 2t, oh, sorry, 2e to the t for this one, times 1 plus 2e to the 2t divided by 1 plus 2e to the 2t. Those cancel. And so the normal component of acceleration is just 2e to the t. And so altogether, our acceleration for this vector function, so the vector function t, 2e to the t, and e to the 2t, this acceleration is going to be given by 4e to the 2t times the unit tangent vector, right? Which we didn't compute, but we were just asked to find these components for it. So I'm just putting it all together here, and then plus 2e to the t times the normal component. So there's our acceleration of this vector function. Okay, so let's leave that one here. Not a whole lot of new stuff in this lecture, just some applications in terms of physics and motion of particles in space. So we'll leave this one here, and I'll talk to you guys in the next one.